All right, this concept of isomerism, it basically tells you about how compounds can be restructured when the number of their formula is the same. So basically, it's the concept of same chemical formula, but they have different structure. So let's take a look at this. Over here, we want to understand what's the meaning of longest straight chain. Now, when you look at this longest straight chain concept, visually you might see that the longest straight chain is this horizontal chain here, which has 8 carbon. But fundamentally, that's not how we will define a longer straight chain. The longest straight chain is in such a way that you can move along, use your pen to trace it, right, without retracing back the path. What do I mean by that? So in this case, right, the longest chain that we have, or the so-called the longest straight chain that we have, comprises of this chain here. So altogether, in this longest straight chain, I have 10 carbon. We have 10 carbon atoms in the so-called longest straight chain. So all this bending, right, when the chain actually bends up. So for example, let's say I have something like this and something like this, or something like this. These U structure, they are fundamentally the same. They are all made up of the longest chain of carbon being 4. So it's 1, 2, 3, 4 here. 1, 2, 3, 4, and 1, 2, 3, 4. See, we didn't retrace back our path. So when the molecule is being bent around, it's fundamentally still the same thing. So that is one of the things that you want to notice for this part of the topic. So as mentioned, isomers, right? Isomers are different structure, but the formula is basically the same. So let's take a look at this. Butane is C4H10. So if you want to draw all the different isomers, the most basic isomer that we will draw is the one that is visually horizontal. So this is our first structure. So how does a different structure look like? So as we mentioned just now, if you feel that this is a different structure, okay, they are not. They are basically the same thing. So we do not want to, when the question asks you to draw an isomer, drawing it this way, right, has basically not changed the fundamental structure of the original butane molecule. They are still the same thing. So how do we normally do it, right? Okay, what I would normally do is I will try to shorten the longest straight chain, or essentially I just detach one of the carbon. So the last carbon I detach it and I put it in the middle. Okay, do not put them on the side, because when you put them on the side, it starts to look like this. Then there's no meaning in it. So if you detach and then you put on the side, they are the same thing. So detach the carbon and then do not put them on the side carbon atoms. Then you will get an entirely new structure. Okay, the key thing is don't put them on the side. So when you look at this is fundamentally very different from the original butane molecule. So in this case, we can say that butane actually has two isomers, or basically two structures that is having the same formula but different structural form. Okay, something like that. So the trick is to detach them from the side, but then put them at the center. Then you will get new structures already. Okay. Anyone with any questions for this? The whole objective is to get a structure that looks entirely different. Okay, if there's no question, uh, yeah, if you put that on the side, you will see that the structure is still the same as the original, because it is still the same as having like this four in a row. You see what I'm getting? So fundamentally, there's no difference at all. So we want to detach them and then reconfigure them a bit. Yeah, so this 1, 2, and 3, they are all the same thing. They are basically the first isomer. This is our second isomer. Understand? So for this butane molecule, there is only two isomers present only. Then what do you mean by put two carbon at the center? So I was saying something like that.
Wait,
Yeah.
like how you know it must have three?
Oh, because I went from 4 to 3, step by step, drop from 4 to 3 to 2 and so on. So it
Wait,
doesn't
so
mean, mm,
is this the longest it can go? Like, is this like the only two isomers?
yeah, because if you drop to so-called 2, right, it will look like something like you have drawn in 1 or 2 already. So in this case, there's only so-called 2 isomers here. Let's look at another example. It will look more clearly. Let's use the hexane example. Hexane is C6H14. Okay, I got a question for this. So if you what happens if you draw it like that? Again, drawing like this it's actually drawing number 1. You see, it's still 4 carbon in a row. There is still 4 straight carbon here. 1, 2, 3, 4. It's fundamentally like this. So the idea is do not you do not get a new isomer if you just literally bend this downwards. Any kind of bending, right? No meaning, because it's still the same thing. You don't rotate them around. You got to literally unplug it and then put it into the middle carbon. Then it will be super safe. Okay, let's look at an example of hexane. Today I won't get you all to draw it. We just draw this together. And then if you all need more practice on this, just let me know. I'll just give you a compound. You can send me all the isomer you think you are testing it for. Okay, so first isomer will be the visually horizontal 6 carbon. Okay, all these I don't draw yet, they are all hydrogen. So this is our first isomer. Okay, the second isomer, how do we do it? So as we mentioned, we will pluck out one of the carbon from the side. There we have 5 in a row. Okay, bear in mind, do not attach the six carbon atom, right, on the extreme carbon. No point, you'll be drawing the same thing again. So I can put it over here. So when I put it over here, you can see that the structure is now entirely different. Okay, so this basically you have a when you plug it this way, you actually have a CH3 structure on carbon number 2. So this is entirely different from the first one. Now, if you were to draw it this way, and you put it over here, okay, these two are the same thing because in chemistry, organic naming, right? You can name your carbon atom number 1, whether from the left or from the right, both are okay. So essentially, these two are still the same structure. Okay, this is basically a CH3 group on the second carbon, but it is very different from number 1. Okay, the next thing that we can do is, again, we avoid the 2 carbon on the side. And then we have explored putting the carbon on the second carbon. But we haven't explored putting on the third carbon, which is here. So this gives us isomer number 3. Okay, as long as you don't attach the carbon that you pluck out, right, onto the N carbon on the straight chain, you are going to get something new. Okay, and bear in mind for the second isomer that we have drawn, putting it on carbon 2 can have these two presentation, can be the second carbon from the left or second carbon from the right. But in chemistry, we don't care whether it's second carbon on the left or on the right because they are still the same. Okay, as of this point, any questions from anyone?
Wait, for this one, so there's 3 isomers, is it?
Oh, way more, way more.
Uh, oh, but like what we have drawn here is 3, right?
Yeah, so far it's 3.
Can you scroll up to the butane one? Why is that one 2 only when we drew 3?
Where do we draw 3? Okay, these, they are all the same.
Wait, why is 1 and 2 the same?
As in,
Sorry, you drew like a purple 1 and 2, like
okay,
the
this
first,
one, these
yeah,
4, they are the same, right?
yeah.
So these are all isomer number 1 only. This is only one isomer. Then the second isomer is number 2.
Oh, is it cause like the fourth C is still attached to the third C?
Kind of lah. They are still the same actually.
Okay.
It's like I normally call it like you bend the chicken wing like that. So you're basically bending chicken wing only. You're not changing the actual
Oh,
structure. You know what I mean? The
okay,
chicken wing,
okay.
you bend it, you bend it, you bend it up, you bend it down. It is still the same chicken wing. You know
Yeah,
what I'm saying?
yeah.
Mm. NC, the idea is you do not any carbon that you detach, right? You do not put it on the N carbon. You put it on the N carbon, no meaning. You're still getting back the same thing. Meaning what do you mean by 3 same as 2? Okay. 3 is not the same as 2. Wait. Okay, if you're talking about this one, then yes, 3 is not the same as 2 because for number 2, the attachment group, right, the CH3 attachment group is attached to the second carbon, while number 3, the CH3 group is attached to the third carbon. So fundamentally, although both of them is 5 plus 1 attachment, but the attachment is at a different place. This is attached on carbon 2, whereas this is attached on carbon 3. So fundamentally, they are still a different structure.
Wait, then is it possible that you bring two carbon down?
Coming to that, that's our isomer number 4. Okay. Firstly, the corner ones, yes. The one on the extreme end, don't attach because no point. Okay, let's look at number 4. Let's proceed with this. CJ, what I'm do if you're a bit lost, never mind, you just take a short break. Okay, so as we mentioned now, we want to change the carbon straight chain. So far we have went from 6 straight carbon to 5 carbon. Then we realize that after we do 5 carbon, we cannot do any more attachment already. So let's try 4 carbon. Okay, so now how are we going to attach the 2 carbon atoms that we have removed? Oh, okay, CJ, good. Then you look at it. Okay, so since we remove from the side, right? Remember, do not connect to this guy. Do not connect to this guy. The moment you connect, it's back to number 5, number 6 again. So no point. So the 2 carbon, we have a few ways to deploy it in the middle carbon atoms. So the only ones that you can deploy is always the ones that is not on the corner. If you're on the corner, then you cannot deploy them. Okay, so this is the most important thing about isomers. So, okay, let me wipe all this away. So where do I put the 2 carbon? Okay, I can put it number 1 this way. I can put the attachment group here. The second one, I can put it here. So you can see this one is basically a 4 straight carbon, and then attachment on carbon number 2, attachment on carbon number 3. Or if you want to see the other way, carbon 2, carbon 3, they are the same, no difference. Okay, so this is I will call a 4 carbon straight with the CH3 on carbon number 2 and carbon number 3. So this is fundamentally different, right? So is there any more ways? Is there any more ways to attach the two attachment group while keeping this to be 4 carbon horizontal straight chain? So the last way we can deploy the last 2 carbon atom, I can put it here and I can put it here. Okay, similarly, if I were to put it here and here, it's the same. Okay, I got no space to draw, I'll just put a CH3, but the idea, you all should know, I'm drawing this CH3 is like what we have drawn previously across the board here. And then you can see that if you number this number 2, you number this number 2, these two are fundamentally the same. Okay, so far hexane, we have drawn 5 structures that are entirely different. Okay, give you a minute to digest. Of course, all the other things I didn't put in, they are all hydrogen. You'll digest this first. Then I'm going to trim it down to 3 carbon straight chain. Because there will come to a point you can't trim any further. So we are going through the process of trimming and see how far we can trim. So give you a minute to digest this part first. Let's trim it down, right? Let's do a pseudo, let's trim it down. So far by reducing the longest chain, right, you see that you actually get new substances, new structures. So what happens if I trim it down to 3? Okay, if I trim it down to 3 straight chain visually, now I got to attach 3 carbon atoms to it. Okay, and as mentioned, we want to avoid the one in the corner. So the only one that we can attach is only this guy only. So I will think that at this point, right, this is the lowest I can trim. With 2 carbon, no point. You can't trim to 2 carbon. Okay, so how many ways can I attach the 3 carbon? Okay, there's only two ways only. One of them is I will connect all the remaining 3 carbon over here, something like that. And the second way is taking inspiration from number 5, right? Isomer number 5, I put one on top, then I put 2 below. Okay, this is also the same as putting 2 on top and 1 below. These two, you all should know it's the same. It's just the second carbon having 2 on top, 1 below, or 1 on top, 2 below. They are the same thing. Okay, so having said this, number 6 looks like we have a few isomers, but it is not true. Okay, there are only 5 isomers for hexane. These two that I have just drawn, they are basically duplicates from the earlier 5 structures that we have seen. Can I give you all 30 seconds? You're going to watch out. Look at the structure. Look at what's the concept of the longest chain. And ask yourself, fundamentally, okay, fundamentally, the two structures that I've drawn, 6A and 6B. Okay, 6A and 6B is actually already drawn from structure 1 to 5. Now I just need you to go and detect, right? 6A and 6B, which one is that? Which isomer are they duplicating? If you can see, that means you understand me. Okay, find the duplicates that is where we have already drawn for 6A and 6B. That means 6A, is it 1, 2, 3, 4, or 5? 6B, is it 1, 2, 3, 4, or 5? The duplicate here is 6A is actually number 2. 6B is actually number 5. Anyone needs me to explain why 6A is actually number 2 and 6B is actually number 5? Oh, NC, I attached at the end to show you that there's no point on attaching it because it is still the same. Then 6B cannot be number 4. 6B must be number 5. Why would you say it's number 4?
Because isn't it like isomer is the longest chain, right?
Mm-hmm.
So like in this case, for 6B, the longest chain is 4 Cs, right?
Correct.
Then isn't for 4 also 4 Cs?
Okay, let's look at 6B. Okay, if you were to okay, you look at this structure here. Look at this structure. Let's rotate this structure counterclockwise 90 degrees. So this one is actually like that. Can you see? And then this and this is actually this and this. It's actually number 5. So even if you rotate this guy, it's the same thing. It's actually this and this. So fundamentally, we haven't done any change to it. Oh, actually, it's here, but no difference. It's still the same thing. Okay, so what we have drawn is actually, let's say this is 5A, this is 5B, right? This is actually 5A, this is actually 5B. They are the same thing. Got it, Zen?
Wait, then what about 6A?
6A, let me explain. 6A is actually number 2, because if you look at the longest straight chain, it is actually like this. So it's actually carbon number 1, 2, 3, 4, and 5. So there's an attachment on this. So technically, right, 6A is 5 in a horizontal row and 1 carbon attached to the second one. It's actually number 2. Okay, something like this. Fancy got it too? Because the bending, again, this is what I call bending. You bending also no, this carbon here, you bending also no point. It is still 5 carbon. All right, any questions from anyone? This one talk so much, also no point. I don't want to spend too much time on this. I can send you all the compound formula after class for those who need it. And then you draw from there. Then after that, we correct and see how many duplicates that you're actually drawn and not sure. Okay, if no questions for this is the idea.
Hi. Wait,
Yeah.
so can I say that like for the longest carbon chain, right, in a
Yeah.
certain structure, right, then it is like the same type.
You got to see where the attachment is also. Like in this case, number 2 and number 3, right? They are both 5 carbon longest one. But the carbon attachment is on carbon 2 and carbon 3. So it's a bit different also.
Oh, okay.
So it not only just the longest chain you change it, where you place the attachment matters. Because if you look at number 2 and number 3, both of them are 5 carbon. But the last carbon we attach to the different carbon, so they become 2 different isomers. Same case for number 4 and number 5. Our longest chain is 4, but the 2 carbon attachment, we attach them in a different way also. That's why it's still different. Okay, something like that. All right, no question. Then let's move over to alcohols. Delcy, you mentioned about a bit unclear last week about isomers. Feel a bit better? Can. All right. Okay, let's look at alcohols. Okay, under alcohols, this is the third the third homologous series that we're doing. We have done alkane, alkene, and then let's look for the case of alcohols. First of all, you have seen in under alkene reaction, they are done when you add steam to alkenes. This is standard reaction. So let's look at this reaction. Okay, addition of steam, you get an alcohol. Okay, we're talking about this. Okay, so since you roughly know how the alcohol is formed, let's go to the naming and all. So alcohol, they are the ones that are formed from the alkene reaction, and then they have a functional group of OH. We also call it the hydroxyl group, and it's fundamentally having this formula, this general formula. So the naming is the same, just like alkane, alkene. The only difference is that for alkane, we ends it with an ANE, alkene ends with an ENE, alcohol ends with an ANOL. Okay, so pretty straightforward. So as we mentioned, first carbon, alcohol, second carbon, third carbon, fourth carbon. So it's the meth, eth, prop, butyl. And because they are alcohol, we end it with a ANOL. Hence, you have all your usual ethanol, propanol, butanol kind of thing. Okay, so that's for the naming. Formula, as you can see, it is CnH2n plus 1 OH. Actually, right, if somehow in the exam you've forgotten how to draw the alcohol structure. Okay, most of you should be able to draw the alkane structure. So draw the alkane first. Okay, so draw 2-carbon alkane. Okay, and so on. So I'll draw until number 3. Okay, how to change it to an alcohol? Remove one of the H. And replace it with a OH group. And when you do this, alamak, I did the wrong thing. This one is structural, damn it. Okay, and this one should be molecular. I did the wrong side. So basically, that's it. We just draw the alkene, then replace one of the H with a OH. You'll get the structure. So formula-wise, okay, you can draw it this way. Okay, what I'm going to show you next is another way to actually write formula. Okay, for ethanol, I can do it as C2H5OH. I can also do it as CH3, CH2OH. Okay, same thing for propanol, C3H7OH or CH3CH2CH2OH. Okay, there is a reason why it's being drawn this way. But for today, I won't tell you the reason first. Just know that it can be written this way. It'll be more useful in for next week's class when this thing reacts with acids. Okay, any questions for this? Okay, if not, 30 seconds, help me copy this down. I'll go to their reactions and properties. Okay, let's look at this. Okay, so as mentioned just now, the alcohols, they are formed from when you take the alkenes and you add steam to it. Okay, fermentation of sugar doesn't give you all kinds of alcohol. Fermentation of sugar specifically produces ethanol only. Okay, so fermentation of sugar, remember, only ethanol. And then CO2 is produced in the process. So let's look at fermentation. So we use yeast, and this yeast, it can actually convert sugar, or when we use glucose, into ethanol. And this is done in the absence of oxygen. Okay, so why absence of oxygen? After we look at the reactions of alcohol, we'll take a look at why absence is needed. And then temperature also shouldn't be too high, optimal at 37 to 40 degrees. Now, whenever we see this 37 to 40 degree optimized temperature, it tells you something about the reaction. Ado, can you hear me? Why specifically 37 to 40? Why is 37 to 40 degree this temperature range significance. What say you? Any idea? No, that is not. No. Yeah, it's not. Yeah, Clarice, correct. Whenever you see 37 to 40 degree, this is a very, I will call it a very biological temperature. Whenever this kind of temperature exists or this kind of temperature appears, you will want to go into enzymes. Okay, your yeast contains enzymes, or you can call it bacteria also can. So this kind of bacterial reaction or enzyme reactions occur most of the time at optimally 37 to 40 degrees Celsius. So two reasons, right? When temperature is too high, normally we use the term the enzymes or the bacteria in the yeast will denature. For those of you who are not familiar with the term denature, it also means they'll be killed. So once that happens, it doesn't allow fermentation to carry on anymore. So whenever you see 37 to 40 degrees, you must trigger some enzyme bacteria getting killed nonsense. Okay, so watch out for 37 to 40. Okay, too high it fails, too low it fails also. Okay, temperature too low. This is the same reason why our freezer helps us to conserve our food. Because when the temperature is too low, the enzymes or the bacteria, they are basically not active. So when they're not active, they cannot carry out fermentation. So this thing doesn't work again. So always has to be 37 to 40, thereabouts. Okay. No question is square D. And they are generally soluble in water. And then your sugar solution also soluble in water. So because of the water over here, it will dissolve your ethanol. Because sugar solution contains water. When you have water over here, your ethanol form will dissolve. So how do you take out your ethanol? Okay, remember when you are dissolved in water, they form a mixable solution. And when you form a mixable solution, the only way to remove two liquids, alcohol and water, that is soluble, the only way to do it is FD, fractional distillation. Okay, one of the good temperatures to remember. Ethanol boiling point, 78 degrees Celsius. Water, 100 degrees Celsius. Do you need to memorize? No, but good to know. So, yeah. So far, any questions from anyone? If not, fractional distillation, why is it suitable? Because this FD, right, suitable for mixable solutions with different boiling point. Okay, the word equation for fermentation. You see what your teacher says, but O level should be all right for both. You can say sugar or glucose. So we already said in front there are two products, ethanol and water, carbon dioxide. The chemical formula, this is the formula, C6H12O6. Ethanol is C2H5OH from the table in front, and we have carbon dioxide. Okay, can I give you a minute to balance this equation? Okay, let's try to balance this. You might find it's a bit hard to balance, but regardless, cannot balance it, memorize off because quite easy to memorize the balance equation, and this is standard. Right, if nothing goes wrong, the balance equation will be 2 in front of the ethanol, 2 in front of CO2. Okay, if you have difficulty balancing this, I highly recommend at least you need to memorize, of course, the formula of the compounds. That one no other way, because this is they are all covalent, so there's no way we can use like ion list and then try to form the formula from there. We can't. So the only way is just to memorize the formula for sugar and everything. The balancing is just a 2-2. Okay, so you have difficulty balancing, just memorize a lot easier. Okay, next. So to save time, I do this with you. Please ignore all this stuff. Okay, so for number 3, we have seen this before in addition of alkene. So let's do a quick one. So condition, not in syllabus, but again also good to know at least is the temperature. 60 atm with catalyst dilute H3PO4. So to get ethanol, we need to use the correct carbon alkene. So ethene 2 carbon, ethanol 2 carbon. And then we have steam, and then we get ethanol. And remember, for addition reaction, there's only one product. Okay, so quick recall over here, CC double bond plus water. Then over here, previously was a double bond. We break the double bond, now it becomes single bond with 2 more extra bonds here. And then one takes the H, one takes the OH. Okay, so this is the structural equation. So formula here, C2H4 plus your H2O to give us C2H5OH. Okay, this is addition reaction, nothing much. Yeah, help me jot this down. All right, let's look at users. Users not important. Just know that all this happened for you, but don't have to literally memorize for it. So primarily alcoholic drinks, number one. Number two, as an antiseptic. And sometimes it's also used as an industrial solvent. And in the same concept of solvents, paper chromatography, we also state ethanol as an alternative solvent in place of water. Okay, so these are I just briefly brush through it. Nothing much here. Okay, let's talk about reactions. Combustion is as usual, your complete combustion and all. Your CO2, your water and all. Okay, but one thing to take note for the combustion of alcohols, right? They are generally very clean. They are very clean compared to alkane/alkene combustion. Generally, they are cleaner. Okay, so for now, I'll be doing oxidation. So, oh yeah, let's do the combustion equation. Pretty straightforward. So product will be your CO2 and water. So for word equation, pentanol, it reacts with oxygen to give you carbon dioxide. Okay, plus water. So this was CnH2n plus 1 OH. So pentanol equation, pent is 5. So it is C5H11 OH plus oxygen to give us CO2 and water. Okay, again, can I give you a minute to balance this one? And because there is a O over here, right, it adds a little different to the balancing technique. Don't neglect the O over there. Okay, for this balancing equation, very logical. You will balance oxygen the last because there's an oxygen here standing alone. You balance everything else, just put a number in front of O2, it is all balanced. So logically, you balance the carbon, you put a 5. You balance the hydrogen. They are all together 12 hydrogen on your pentanol, 11 plus 1. So total 12, I put a 6. So by doing this, all the carbon and hydrogen are balanced. Okay, so let's put a number in front of O2 in order to balance everything. So on the product side, you see that there's a total of 10 plus 6, 16 oxygen atoms. Okay, so to balance on the left-hand side, because of the O, I will just need to assign um, 15 oxygen over here. Now, because this is O2, I put 7, not enough. I put 8, it will exceed. So the way to balance this is to put 15 over 2. Because 15 over 2 times 2 gives us 15. then plus the oxygen from your pentane is all balanced. Okay, so this is our balance equation. But of course, we cannot be using a fraction. Okay, those who are doing higher level chemistry, you will see that balance equation it's okay to be in fractions, but not at our level now. Beyond, next year you will see using fractions as a means of balancing equation. So it is good to understand how I get 15/2. It will help you a lot in your balancing next year. Those who are doing A-level chem, confirm you will see fractions. Okay, but just use the fraction. Fraction is just a number for you to balance this kind of odd number stuff. But for us, we got to remove away the denominator, 15/2. So we balance it by multiplying 10 throughout. Sorry, multiplying 2 throughout. So after multiplying everything by 2, I will get 2, 15, 10, and 12. This is the actual balance equation. So the mole ratio is 2:15, 10, 12. Okay, so that's the mole ratio. That's how we will balance it. All right, any questions for combustion balancing equation for alcohols? All right. Okay, let's look at reaction number 2, oxidation. So what are the oxidizing agents that can oxidize your alcohol? First of all, is oxygen in the air, specifically oxygen gas. Okay, the other two oxidizing agents that we use frequently will be your acidified potassium manganate, KMNO4, and dichromate, K2CR2O7. Color changes when it happens purple to colorless, orange to green. So during the oxidation process, okay, we convert it to butanoic acid, and water is also produced at the end. Okay, nothing much here. Chemical equation, let's proceed to acid first. So from the acid part, right, then we decide how to get the formula for the respective acids. Okay, I'll leave this screen here a minute, you all jot down everything. A minute's time, I'll move over to acids. Then from the acid, we will get the formula. Then we come back to this again. Right. Let's go to acids first. Right. Organic acids, all of them have the COH. This is our fourth homologous series after alkane, alkenes, alcohol, the fourth group acids. So the formula, you notice the general formula starts. Traditionally, if you try to memorize this formula and try to use it, it's gonna hurt. Because we don't use this formula all the time. So it's a bit hard to see. Oh, Renee, I just saw your message. No, dichromate is a oxidizing agent, so he gets reduces. So it's not he oxidize some stuff, but he get reduced. The potassium manganate also the same thing. It's an oxidizing agent, so after the reaction, it is reduced also. Is it okay? Okay. Okay, so if I don't want to use the formula first, right? Okay, we don't want to use this sucking formula. How are we going to use? How do we get the formula for acid? So to do it right, the easiest way, this is what I normally do, even up till now. Okay, I'm still using this method. And I've never made a mistake with the formula. So in order to do it right, okay, the naming wise, same thing. Meth is prop mu for the first four. And then we attach ethanoic acid to it. So this become methanoic acid, ethanoic acid, propanoic, and butanoic. Okay, so to get the formula, normally I'll draw the structure first. And no matter what number of carbon atom, I always begin it with the structural formula. Okay, this is your COOH. It looks like this. Okay, we have done this on the first page of the notes, just a recall. So do the same thing. Okay, and then you will go on to add in the number of carbon required for you to achieve the acid. So methanoic acid, there's already one carbon. Okay, this carbon is also valid. Okay, all these carbon, they are all valid. So the first carbon already present in methanoic. So I think in organic chem very simple. If you don't know what to put, just put hydrogen. So it will work. Okay, so the formula here, simple, HCOOH. Ethanoic acid, add 1 more carbon. Propanoic acid, add 2 more carbon. Butanoic acid, add 3 more carbon. Okay, then every carbon you know needs to form 4 bonds. So there's already 1 here. So add another 3 more. So the formula becomes CH3COOH. Okay, same thing over here. This carbon needs 3 more. This carbon needs 2. So my formula, again, I show you the 2 ways it can be done. C2H5COOH or CH3CH2COOH. And same thing for the last acid, C3H7COOH or CH2CH2CH2COOH. All right, so for the chemical, we already know butanol formula. So butanol formula is 4, so it's C4H9OH. Okay, how do we introduce the oxygen? Normally, you can put it as 2O, and then the formula for butanoic acid, we have C3H7COOH, and then plus water. Okay, it can be presented this way. Okay, notice this is plus O2. Combustion also plus O2. Then how do I know which one is they're talking about? So you need to understand, are you doing combustion? If you are doing combustion, then your butanol turns into CO2 and H2O. But if you are doing, like this case, oxidation process, then your product will be an acid. Okay, so just know, just understand what is the purpose of the reaction. If you are doing combustion, then you get CO2. If you are doing oxidation, you get an acid. That's all. Okay, let me give you another possible presentation that you might be seeing also. Sometimes your paper may give you something like this, but same idea. They give it to you as 2, and they put a bracket O. It's like 2 oxidizing agent. But to introduce to it, right? Because ultimately it's still a balanced equation. It's ultimately still O2. But it's just a different presentation. So don't be shocked when you see this. They are the same as O2. Okay, then from here we get C3H7COH, same deal, and then water. Okay, please help me jot this down. Then we'll go back to the previous page, answering why oxygen cannot be present during fermentation process. Now it should make total sense, really, because when you undergo fermentation with oxygen present, as we can see in point number 3, your ethanol produced may get oxidized. Okay, it may get oxidized to form ethanoic acid. Okay, so let's go back to why oxygen must be removed during the reaction, because the presence of oxygen Oh, what is this shit? Oh, I haven't seen this for a long time. Oh, let's see what we lost. Damn it. Yeah, just this equation. Okay. Okay, so as mentioned, we do not want oxygen because it may cause your ethanol. And one of the things that we use ethanol for is a beverage, which is your all the alcoholic drinks. So if it gets oxidized to this, right? This in the form of alcoholic drinks, okay, it may turn the drink to be sour because of the presence of ethanoic acid. It may cause the drink like the wine and all to be sour. Okay, just put a note there. Okay, the next question I'm going to add in over here is when you do fermentation, right, it is almost impossible to get pure ethanol. It's impossible to get pure ethanol from the fermentation process. And it's not because this is a reversible reaction. That means at some point of time, right, your fermentation process will not be able to produce 100% ethanol, which means not all the sugar is converted to ethanol. So I need you to think about why. Why is it that you cannot obtain pure ethanol strictly from fermentation? In fact, let me put it here. Okay, why is it that the fermentation process we cannot obtain pure ethanol as a product? In fact, when you do fermentation, right, normally when you get about 16 to about 20-ish% of the mixture, if it reaches about 20-ish to 16 to 20-ish% of the mixture being ethanol, the percentage cannot increase anymore. Which means you cannot reach a point where you get 100% ethanol present. Even if you look at it, if you look at certain alcohol, for example, okay, those industrial alcohol, they can go up to maybe in your container, it says maybe 60% ethanol, for example. But over here, we say that we can only get 16 to 20%. So normally how this is done is that, first of all, we do fractional distillation to obtain 100% ethanol. Then we add H2O to dilute it to 60%. That's how we get alcohol concentration to be higher than what the yeast can do. Okay, so the idea is that we cannot get pure ethanol during fermentation. So my question for you is why? Your answer all lies with the users above. You look at the users above, one of the things that was the use, okay, normally users not important, but I include it because of this particular question. Antiseptic. Okay, alcohols are being used as antiseptics. And because it's an antiseptic, it kills germs. What are germs? Enzymes. So you cannot get beyond this because at about 16 to 20-ish%, the alcohol concentration is too high. Okay, for the if it's too high for the bacteria in the enzyme to survive. So essentially, right, you're producing so much alcohol. The alcohol that you produce, if you are the bacteria, the alcohol that you produce killed you. Basically, you produce so much alcohol that the environment becomes inhabitable for the enzyme. So the enzymes get killed by it. So how do you go beyond that? Because beyond that, the enzymes cannot do it anymore. So we will do fractional distillation to get pure ethanol, and then we add water to dilute to the percentage that we want. Okay, so please help me jot this down. Okay, weak acid. So we will mention about this thing here. They are acids that undergo partial ionization. Okay. Next, let's look at, because these reactions these are essentially chemical properties. Let's talk about physical properties. So I'll just I'll write down the answer for chemical. These are very straightforward also. So while you are recalling what are the physical properties, so A to E you have done before, A to D you have done before. Acid reactions always produce a salt. And these three reactions, they have water, and because you are carbonate, you contain carbon dioxide. Okay, nothing much here. And metal reaction produces hydrogen. Okay, the only thing new here is acid reacting with an alcohol. Not any acid, it must be organic acid. Your HCl, all these I cannot do it. Only your organic acid reacting with alcohol, you get something called ester, and you get water produced. Okay, that's all for the chemical properties. Okay, so recall your physical. I'll go through in a minute. Physical properties. Those that are confirmed physical properties. Number one, good electrical conductors. Okay, you have seen this in all these acid being electrolyte in electrolysis. So they are good conductors because of the free moving H plus ions. Number two, sour taste. Okay, these two I will put it under very, very strong physical properties. They are very strong answers for physical properties. Now, if you have other things like turn red litmus blue, I'm sorry, turn blue litmus red. Okay, my stand on litmus paper, is it a property? Okay, to me, property is not a reaction. So when we talk about properties, if you can turn something from blue to red, that a bit feels like a chemical reaction. So normally I will not want to commit to the color change of litmus for physical properties. So I'll try to avoid that. So my two strongest answer for you for physical properties, these two. These two are always correct.